Hello everybody. In this session, we are going to learn about dual input, balanced output, differential amplifier, DC analysis. At the end of this session, students will be able to analyze the dual input, balanced output, differential amplifier for its DC operating conditions. This is the content of this session. Now, let us start with the definition of DC analysis. What is meant by a DC analysis? Whenever any circuit is analyzed considering only DC voltages and DC current, so that is called as a DC analysis. So, DC analysis, to perform DC analysis, we need a DC equivalent circuit of the basic circuit. So, steps to perform a DC analysis: obtain a DC equivalent circuit by reducing input AC voltage signals to 0. And what is the purpose of DC analysis? By performing a DC analysis, we can derive the equations for collector current ICQ and collector to emitter voltage VCQ. Now, this figure shows the circuit diagram for basic dual input, balanced output differential amplifier. The circuit is designed using two identical common emitter biased transistor amplifiers using the transistor Q1 and Q2 of same type. The proper working of this differential amplifier, the magnitude of biasing voltages plus VCC and minus VEE must be equal and of equal and opposite polarity. The components in the each half section of this differential amplifier should be similar to other half sections. So, circuit should be bilateral symmetrical when the two input signals are applied to the differential amplifier. Now, let us convert this basic circuit of a differential amplifier to its DC equivalent circuit for a DC analysis. So, the Vin1 and Vin2 are input AC voltage signal sources. Rin1 stands for internal source resistance of first input signal source Vin1, and Rin2 stands for source resistance of the input signal source, AC input signal source Vin2. Output is taken between the collectors of a transistor Q1 and Q2. So, the final output voltage is the voltage taken at the collector of Q2 with respect to voltage at the collector of Q1. Emitter resistor R is connected to the common point of emitters of two transistors Q1 and Q2. So, that is used to bias the emitter base junction of transistor Q1 and Q2. So, each half section of this differential amplifier must match with the other half. Now, this figure shows a DC equivalent circuit for basic dual input balanced output differential amplifier, in which the input signal voltages, AC voltage signals Vin1 is reduced to 0 and Vin2 is also reduced to 0. So, in the circuit diagram, there will be only source resistance Rin1 and Rin2. IB1 is the current flowing through base of transistor Q1, and current flowing through collector of transistor is IC. Current flowing through the emitter of transistor Q1 is I1, and the current flowing through the base of transistor Q2 is IB2. As circuit is bilateral symmetrical, we can derive the equation for one of the half section for considering only one transistor, and those equations can be used for other half sections or other transistor of this differential amplifier. So, let us derive the equation for transistor Q1. So, let us first go for collector current ICQ. So, apply KVL to base emitter circuit of transistor Q1. So, using Kirchhoff's voltage law, we can write a voltage equation minus Rin, as Rin1 and Rin2 are equal, we are designating as Rin into IB minus VB minus RE into 2I plus VEE equal to 0. But IB equal to I upon beta DC. Since the emitter current I is approximately equal to collector current, so replace IB by I upon beta DC. So thus emitter current through transistor Q1 is given by I equal to VEE minus VB upon 2RE plus Rin upon beta DC, where VB is a cut-in voltage, base emitter junction cut-in voltage of transistor. So that is a 0.6 volt for silicon transistor and 0.2 volt or 0.3 volt for germanium transistor. So generally value of Rin upon beta DC is much less than 2RE. Therefore, for simplicity, we can neglect that Rin upon beta DC. The equation is simplified to I equal to, that is the emitter current I is approximately equal to VEE minus VB divided by 2RE. Let this is equation number 3. So using equation number 2, we can calculate the exact value of emitter current I, and using equation number 3, we can calculate approximate value of emitter current I. So equation number 3 indicates that the desired value of emitter current I can be set using emitter resistor RE for a given value of VEE, and emitter current is independent of a collector current. Emitter current is independent of a collector resistance RC. Now let us go for collector to emitter voltage VCQ at Q point or DC operating point. Assuming a voltage drop across the source resistance Rin is negligibly small, for simplicity we can neglect that. The voltage appearing at the emitter of transistor Q1 is approximately equal to minus VB. Using Kirchhoff's voltage law, the voltage at the collector of transistor Q1 is given by Vc equal to VCC minus RC into IC. Let equation number 4. So voltage at collector with respect to ground, so that is equal to VCC minus RC into IC. The voltage between a collector and emitter is given by, so voltage at collector with respect to emitter Vc, using KVL we can write Vc equal to, so that is equal to Vc minus V. So that is voltage at collector minus voltage at emitter. So Vc equal to, for Vc we can write VCC minus ICRC, and for V voltage at emitter we can write minus VB. So VCC minus RCIC minus VB. So the final equation for collector to emitter voltage, Vc equal to VCC plus VB minus RC into IC. So in this way we got the equation for collector to emitter voltage at a DC operating point or a Q point. So using a DC analysis equation number 2 and 5, the DC operating point values for VCQ and ICQ can be obtained, and the emitter resistor RE sets up a desired value of emitter current for a given value of negative DC biasing supply voltage minus VEE, and emitter current I is independent of collector resistor RC. So these equations can be applied to all configurations of a differential amplifier, like a dual input, balanced output, unbalanced output, a differential amplifier, dual input, unbalanced output, a differential amplifier, single input, balanced output, a differential amplifier, single input, unbalanced output, a differential amplifier. As emitter current is constant, so the Q point is stable. So in this way, by performing DC analysis, we got the values for DC operating point, like output collector current ICQ and output collector to emitter voltage VCQ. Now students can pause a video here and try to answer this question. What is the significance of DC analysis of a differential amplifier? So DC analysis is nothing but whenever circuit is analyzed considering only DC voltage and DC current, so that is called as a DC analysis. So DC analysis is performed uh, using a DC equivalent circuit, and it is used to obtain DC equations for the basic parameters of that circuit, like the DC operating point or quiescent point values for output collector current ICQ and output collector to emitter voltage VCQ. So this is a reference. Thank you.